Hey everyone, welcome to the LocalStack community meetup for the month of October. I'm just so excited to be back to be hosting again, and it is just so good to see some new speakers joining us today to talk about how they can drive chaos and resilience testing with LocalStack. I believe I missed the last meetup where Brian was hosting Varian, who was talking about Chaos API and how you can do chaos engineering with LocalStack. And we just thought, like, let's have another meetup where we can bring some of our partners who can also talk about how you can use their software developer toolings to also drive chaos and resilience testing. So here we are. Welcome once again, and thanks for being such a supportive member of the LocalStack community. So just to talk a bit about the agenda for the day, we are going to have a really short intro and welcome. So you're going to see some new faces for this meetup, some new speakers joining us from Antithesis and CockroachDB. The first talk is going to be about autonomous testing AWS apps with LocalStack and Antithesis. This is a really exciting topic for me because autonomous testing, that's a new concept. I definitely want to explore that up and see how Antithesis is helping us around. The second talk is going to be around CockroachDB. I had some really nice experience like dabbling with CockroachDB since my university days. So I'm just so excited to see Rob talk a bit more about the tooling and how it is helping us like today. And also excited to see how LocalStack kind of integrates with CockroachDB workflows. So with this, let's bring the speakers on the stage. But yeah, just one thing. Yeah, let's bring the speakers on the stage. I guess I just forgot about the other slide. So hey, Rob. Hey, Ben.
Hello.
Hey,
Hi,
Gabriel.
everyone.
Cool. It's so great to see all of you here. How are you doing?
Very well, thank you. Thanks for having us.
Definitely. And what about you, Ben and Gabriel? How's the weather over there?
It's really great. Thank you.
Surprisingly nice.
Yeah, surprisingly nice. I just hope that you don't headbutt each other quite often during the talk, and it really goes
The
nice.
first half is the
This is
second half, so
yeah. So this is the first time we are actually doing it in such a way. So that would be pretty exciting. And before having this meetup, I was actually talking with Rob about his tattoos. So Rob, I guess please tell us about that. What's your favorite bug that has been emboldened as a tattoo or something?
Well, I get this is my ode to code tattoo arm. You'll see a big cockroach there, and there's a couple of CockroachDB tattoos.
Yeah.
But my favorite bug is this one, minus 32,768, and it refers to a bug that I encountered many years ago. The team created a table that could store 32,000 of a particular type of event, and we had a very busy day, and we ran out of rows in that table. We hit in basically int 16 max value. And I could have fixed it by changing the database and changing the code with a bunch of downtime, but my fix was disgusting, and I remain very proud of it to this day. And that was simply to resequence the index to minus 32,768 to fix the bug live. So we just started to see really random negative numbers for IDs for a little while, but it bought us about 6 months.
Mm-hmm. Wow, that's pretty interesting. Thanks for sharing that. Yeah, I guess we can do like a basic round of introductions. So maybe Ben, Gabriel, you want to go first?
okay. My name is Gabriel, and I just started 3 months ago here, and I'm doing developer relations.
That's
Yeah,
awesome.
and my name's Ben, and I'm a senior software engineer at Antithesis. So.
That's awesome.
And hi, everyone. I'm Rob Reid. I'm technical evangelist at Cockroach Labs.
And yeah, it's so exciting to see Rob, like you have so many bugs. This was something that I was not aware about just before yesterday. So yeah, just so excited to see all three of you talk and yeah, share your insights and experiences with us. So yeah, let us go back to the slide deck and let us actually look at the Slido link for the day. So as always, we always do our Q&A on Slido. It's an anonymous platform where you can post all your questions, and we'll be more than happy to have our speakers answer those questions for you. So whatever questions you have, technical, theoretical, or conceptual questions, just put it over there, and we will definitely take a look at the end of your respective talks. So with that said, I guess I won't be just beating around the bush any longer. I'm just going to give the stage to Ben and Gabriel, who would be talking about autonomous testing AWS apps with LocalStack and Antithesis. So let's go.
Hello, everyone. Can they see the slides? Okay, perfect. Let me just double check. Awesome. Well, thank you, everybody, for joining. As he said, we're going to be talking about autonomous testing AWS apps, in particular, serverless apps. And one of the main goals of this talk is to really understand why building service applications is inherently complex. And for that, we're going to take a look at the poster child of serverless computing, which is AWS Lambda. At its surface, we're given a function, but behavior-wise, it's nothing like the function that we would write locally, or even a server that we would run on an EC2 instance. And partially that's because underneath the hood, an AWS Lambda is nothing like a function, but it is a highly distributed multi-tenant service that looks something like this. Now, in this architecture diagram, the part that really matters is this section right here, which shows the shared scale to zero pool of workers that really enables this pay per request model. But this shift from an own long-lived resource to a shared short-lived resource, while great for operational complexity or reducing that, and also for reducing costs for workloads, it does make distributed system challenges a day one issue for devs, even for the simplest of apps. Now, what do I mean by that? Let's look at a few scenarios that a developer would have to handle, and this shows kind of the pros and cons of this architecture. So again, because of this shared scale to zero model, we get a very cheap pay per request, and we get to not have to think about infrastructure from an operations point of view. But that does mean that this pool of workers does come with constraints and limitations. And a lot of this manifests on the developer. They have to think about cold starts in terms of latency. They have to think about time limits on their execution. And they have to think about throttling because of the concurrency limits that are given on the workers. Another pro is just the isolation and parallelism of Lambda. So by default, each concurrent request is spinned up on a different worker. Again, this is done for security reasons and also just for throughput. But this does mean that a developer has to think about idempotency on day one, unless they want to have race conditions. And this could be a non-trivial task, especially if you have a pure function that doesn't interact with many other servers. But if your Lambda, like most Lambdas, is interacting with other distributed services, is making some state changes, you're going to require something like an idempotency table in a separate database that now you have to host, and idempotency keys to go along with that. On top of that, Lambdas are highly scalable and reliable, but with this comes a lot of distributedness. And this distributedness means you have to deal with network faults. And practically speaking, your code, this requires a retry policy, adding timeouts so you don't deadlock your system or reach the execution time limit, and even deal with error handling in terms of partial failures. Now, am I saying serverless is bad? No, not at all. As we talked about, it's great for reducing operational complexity. You don't have to manage infrastructures directly. And it's great for reducing costs, especially if you have irregular workloads. But what I am saying is bad is this combinatorial explosion of all possible interactions and fault scenarios that a developer has to think about. And the first question I'd have if I saw this is, which combinations harbor a bug? Well, I have no idea. And I really doubt that your n number of test cases do as well. On top of all of that, capturing this real world complexities in your test is very hard. And it's not just hard to predict, but it's also going to be very hard to replicate. So the ideal situation would be if we could just test in prod all the time, right? We would get maximum realism. But how can we test in prod without actually testing in prod? That's where autonomous testing provides a really good solution. So Antithesis autonomously tests software. And at a high level, what we mean by that, we're asking you not to write tests, but to generate them. And in Antithesis perspective, we're saying have us generate them. Now, a slightly more technical definition of autonomous testing might be that we simulate the possible interactions and fault scenarios without you having to think of every individual scenario yourself. Okay, but how does it work? You know your software, how your software should and should not behave. Tell our platform that, and it will generate tests that both interact with your software while simultaneously injecting faults to verify correctness. But how does it really work? If you wanted to start generating tests, you would trigger a test run. This could be something from like a GitHub action. This would send your software under test to us under containers. These containers are then spinned up in our specialized virtual machine, and then the simulation can begin. We can start interacting with your software and injecting faults. Some of the easiest faults we can do are just simple network failures, slowing down packets, causing network partitions, simulating outages. And this is where most fault injectors stop. They do a little bit of network failures, they do a little bit of crashing of the containers. But our fault injector goes one step further. Because we have so much control over our virtual environment, we can do stuff like this. we can pause your threads to kind of cause interesting interleavings, see if there's race conditions in those interleavings. We can reduce the percentage of CPU that your, let's say, your Postgres or your container gets, simulating a throttling. We can even change your sifting clock and see how your application reacts to that. And finally, we can modulate the CPU, which means we can slow down and speed up the CPU clock, again, to force interesting interleavings and tease out some race conditions that might exist. Now, there's one thing I glossed over this, which is, what do I mean by specialized VM? By specialized VM, I really mean deterministic VM. And by that, I mean that your test run is going to have a total order of events by the end of it. And the reason that's really interesting is because you can then reproduce your bug. And so let's say we ran a simulation, and by the end of it, we found an interesting bug. Lots of these bugs are really hard to reproduce in the wild because of a lot of non-deterministic behavior. But if you run your test in our virtual machine, we can easily reconstruct the sequence of events that led to that bug, helping you fix it a lot faster. Now, what's the price of this determinism, though? The price of this determinism is, unfortunately, we haven't figured out how to control the real world or make the real world deterministic. And so for now, there is no internet access. Now, you might be thinking really quickly, what about third-party dependencies? If you can containerize your third-party dependencies, no problem. You load them into our VM, we run your simulations, and we find bugs. So these are stuff like Postgres, Kafka, anything that could be containerized. But again, you might be thinking, what about things we can't containerize? The short answer for that is mocks. The medium answer for that is preferably realistic mocks. And the long answer of how we would mock something like AWS, I'll pass it on to Ben. Thank you.
All right. So Gabe mentioned that having deterministic simulation testing gets us all of these really good things, right? We can explore the really complicated state space of a really distributed application by injecting specific faults and finding ones that lead to really nasty, unpredictable bugs, right? And then once we do that, because it's deterministic, we can replay that exact series of events to find and debug that bug. But the big trade-off is that the internet is about the least deterministic thing you could possibly imagine, right? Everything is changing out in the real world. So we are left to mock any services like AWS that do require internet access. And how might we do that? So in a world without LocalStack, or where we hadn't heard of LocalStack, we would do something like make a very simple local mock to replicate our serverless function. And what this might look like is spinning up a statically running server that takes in requests with the same shape as your serverless function and then invokes that function's code locally, right? And this is really not that bad of a thing to do. It's very implementationally simple, and it gets us something that we can put under simulation testing fast. Because of that simplicity, it's also unlikely to introduce additional bugs into your application from you kind of mocking AWS's environment in a buggy way. But the biggest problem here is that it's not realistic at all. It's not faithful to what's happening when you actually invoke a Lambda in the cloud. And this is because of all the reasons that Gabe showed you in the first half of this talk, right? Real serverless has a lot of inherent complexity that is not accounted for by something like this mock. What do I mean by that? What specific ways? I want to dive into three. So we have the respective latency behaviors of a serverless function versus the naive mock that we talked about a second ago. Same with the scaling tendencies and also just the existence of these services on a network. So the first big difference is in latency. And this requires a little bit of an overview of what happens when you actually invoke a Lambda function. And so when you go to invoke a function for the first time, AWS provisions you a new execution environment that can serve that function. So it does this phase over here with the white boxes, which is the initialization phase. AWS says this usually takes somewhere between 100 milliseconds up to a second. And then once that initialization is complete, it's able to actually invoke your function in the yellow box. So if you have a particularly short running function, like something that just signs a key or does one table lookup, this initialization phase can end up taking 99% or even more of the total runtime that you're paying for of your function, and thus your total latency. The benefit is that, after this, what's called a cold start, if you invoke that same function a couple of times after, while that execution environment is still live, you have a warm start. So that function can be reused, and then you're really only paying for the code that runs, and your latency is going to be a lot lower. So this makes sense, right? This is how AWS enables a shared tenant, multi-tenant architecture like Lambda to exist. But it does have some latency consequences that we need to think about when we're mocking this function in a much more simple way. In particular, if you look at this chart on the left, this is what your latency would look like in kind of a hypothetical scenario for your naive server mock, right? It's tightly clustered around a low latency peak that is just the execution time of your function itself. In the serverless world, though, you have two peaks, right? You have one distribution of latencies that come from your warm starts, another much higher distribution of latencies that come from your cold starts. And the worst part of it all is that when you go to invoke a function, you really don't know which of these types of distributions you're going to be pulling from. And we found this to lead to some really interesting, well, concurrency bugs and race conditions, depending on if they happen in prod or not. The second big difference is in the scaling behaviors of these functions. So in a naive mock, as you continue to add concurrent executions, your server is going to be under more and more load, and your performance is going to start to gradually degrade with the increased number of concurrent invocations. But serverless has a different model. One of the chief advantages of it is its burstability and elasticity and scalability. So for a while, as you continue adding function invocations, as you continue adding concurrent requests, you're not going to see a lot of in your performance. But AWS does set a hard limit on the number of concurrent function invocations that can be running on your account at one time. This defaults to 1,000, but is adjustable. And if you end up going over that limit, all subsequent function invocations end up getting kicked into a queue with a pretty aggressive exponential backoff that in practice is going to cause your execution times to really grind to a halt. This is something that you definitely want to avoid if you use Lambdas for a lot of critical services. And it's something that you can't test in this naive mock. And finally, networking behaviors, right? When you take a piece of your software, something that your core software product is already doing, and kind of externalize that to a serverless function, you're adding an edge in your network graph. And like Gabe talked about earlier, lots of faults and messy network inconveniences can happen along that edge. And so you need the ability to test that, inject faults along that axis using a tool like Antithesis, and kind of adapt your retry logic accordingly. And this is something that is not as easy to test with that naive mock that we talked about earlier. So what do we do, right? In a worse version of the world, each company would have to write a version of this themselves that is more faithful to the underlying execution model of AWS and mimics its API and all of its behaviors. But thankfully, we have LocalStack, which is great. And the key advantage of LocalStack, in addition to the fact that it is a much more sophisticated emulator of the full cloud, mirrors AWS's APIs in a lot of really convenient and compelling ways, is that it dynamically spins up Docker containers on the invocation of new functions, right? So it does this same cold versus warm start behavior that we're so interested in observing from a serverless function, because it will spin up a new Docker execution environment for you if you need one. Otherwise, we'll reuse one that's already warm. You also have the ability to configure this Lambda concurrency throttling through an environment variable, and you can even set it very low to something like 5 or 10 to be able to observe the failure case when you overshoot your Lambda budget. And finally, since each Lambda container is being spun up independently as a container on a network alongside the rest of your software and the LocalStack container, you can practice injecting network faults and building resiliency to those between them. So this is why we think LocalStack is really great and why we use it in our mocking at Antithesis. Simple mocks like the one we talked about ignore a lot of the inherent complexity that Gabe and I have talked about in serverless applications. And we have found that ignoring that complexity leads to missing a lot of really crucial concurrency and fault tolerance bugs. And so this is why we think LocalStack and Antithesis make such a great duo. LocalStack allows us to have a way that we can replicate in an offline sense the complexity that's underlying a lot of AWS services because of their realism and faithfulness to the underlying execution model. And Antithesis gives us the opportunity to actually explore that state space, inject faults like crazy, and then find and replay the interesting states. So we've talked a lot about the complexities of serverless, obviously. And I think it's very reasonable to say, okay, these are very small execution model differences. Are these actually things that are likely to cause bugs, or is this just kind of majoring in the minors? And we've been running some experiments, building a new product at Antithesis that is actually proving that this is really where bugs love to live. So we are building a database from scratch for expressing the queries that we write for our data internally from our testing experience, getting those to run much more quickly and effectively. And we have committed since day one to testing this database internally with LocalStack and Antithesis. So we're kind of building this and fault tolerance testing it using LocalStack and Antithesis as we go. This database makes very heavy use of serverless compute, especially to fulfill queries. So this is an architecture diagram, and you can see that there is a fleet of Lambda workers. And when one of a variety of query coordinators receives an incoming request, it will spin up basically as many Lambda workers as it's allowed to, and send those off to fulfill independent parts of the query and aggregate back up the results. So because of all of this, because of this dynamic use of serverless compute, we are really living in those three sources of complexity that we've talked about, right? The latency, scalability, and network faults. In particular, the bimodal latency, since we are executing queries here, we are very latency sensitive, and it's one of our main goals to be able to execute these as quickly as possible. But also, we are, as we said, kind of frequently bursting up and spinning up lots of new workers at the same time, which means that we're going to have a very high percentage of cold starts, higher than most applications and higher than AWS suggests in its typical studies of these things. So that's something that we have needed to account for from the beginning for both performance and correctness reasons, and LocalStack helps us do that in our simulated environment. The second was the hard ceiling on scalability. So as I said, to fulfill these queries as quickly as possible, we want to maximize our Lambda concurrency. But even more important than doing that is not getting the rest of our Lambdas in our account throttled, because we use them for a lot of critical services. This actually led to us adding a rate limiter for these Lambdas that does some really complex concurrency accounting. So you can see how these serverless complexities are actually influencing the design of what we're building. But we also need to be able to test things like this rate limiter with something like LocalStack in Antithesis. And finally, these network faults, such as between a Lambda and the coordinator that requested it, between the coordinator and a rate limiter, make that rate limiter's job much harder. As in the presence of an unreliable network, it becomes a lot more difficult to understand how many Lambdas are running, what data they're processing, and how long they've been running for. So we started spinning up this database, and we did kind of our early manual smoke tests, like the naive mocks, basically, that I said earlier are not so good of an idea. And those were green, and we would even try to mess around with them and do some semi-manual testing. We weren't really able to shake out any bugs. And then we threw it and did a long test run simulating a bunch of crazy fault scenarios in Antithesis, using LocalStack as the AWS engine to mock those Lambdas, mock that serverless compute engine, and bugs absolutely fell out of the sky. So one of the really cool concurrency bugs that we saw early on in the development of this that I want to share with you is related to this invariant in our product that says we have at least as many running workers as workers that are scheduled to be killed. So basically, these workers are the Lambdas. And what we're trying to prevent here is a situation where we request to shut down 5 Lambdas, but we only have 2 available, right? That's a strong indicator that something has gone very wrong in our concurrency accounting. And it means that something needs to be accounted for and maybe made more atomic or something like that. So as you can see, this is a report that we ran and found that this property was failing. And not only was it failing, but it was failing in a very catastrophic way, right? We were requesting, 4.3 billion workers to be shut down, which a very heavy traffic day would have taken an extremely long time to kind of fulfill all of those shutdowns in production. So what did we do about this, and how did we get here? Well, as Gabe was talking about earlier, the advantage of doing this testing in a deterministic environment is that we can take this bug that happened at t equals 571 seconds into our experiment. We can go back to right before it happened and step through all of the things that led to this bug. We can also change history a little bit there and see what would cause the bug and what would fix the bug. And so as we walked back through those steps, we found this sequence of events. The first thing that happened is we requested a Lambda invocation in response to a query. And we could see from the LocalStack logs that this Lambda invocation, there was not a Docker container ready. So this required a cold start. So it's going to take longer than usual, right? Then the rate limiter felt that we were nearing our concurrency limit. Remember that second issue, and requested that that worker be canceled before it was done with its cold start initialization. So kind of changed its mind. Because of that, we had 2 different state updates to make. These are state updates that were at the time that this bug was found, not atomic, but have since been made atomic. And the first one was to increase the number of Lambdas that were scheduled to die. So we did that. And then this Lambda that's been cold starting since step 1 finally is able to connect, and obeying the instruction limiter immediately disconnected after that. Then we would usually make the second half of our state update, but we had network faults and we lost communication with our rate limiter. And so the coordinator was left on its own to decide how many Lambdas it was supposed to request the cancellation of. And because that state update, the other half augmenting the number of Lambdas that were running, had not completed, we ended up calculating the number of Lambda invocations that needed to be canceled as 0 minus 1. And because we were working in Rust with unsigned 32-bit integers, this caused an underflow and led us to try to cancel 4.3 billion lambdas, which, as I said, would have been a very bad day if this had made it to production. So we looked at this bug kind of in awe, and we're thinking about it, and we're like, we feel really confident that we would not have been able to write an integration test that could catch this bug. Like, even if we thought about the exact fault scenario, it would be so hard to get the specific timings right to be able to reproduce something like this. But also, if you imagine this software running in production, servicing customer queries for long enough with real network weather, it's very feasible to imagine something like this happening. Right. So we think this is the real strength of testing with Antithesis and LocalStack, being able to model and simulate that complexity and find these really nasty bugs that are kind of unique to serverless applications. So we hope you've learned a lot about that, and we hope that your serverless bugs will also stay just funny testing stories. Thanks, and we're happy to take any questions.
That sounds awesome. Thanks a lot, Ben and Gabriel, for just walking us through LocalStack and Antithesis. I kind of went through your website, read a bit of the docs, but I was still just on the loop about what autonomous testing is. And this talk was really insightful for me, really something that would help me just get started up really, really quick.
Amazing.
So we do have not a couple, but actually a few questions up on our radar. So let's go over them one by one. So the first question, how can we get started? Yeah.
So the way you get started is right now, the initial step is a bit manual. So you have to contact us to kind of set you up. Once that initial setup is done, then you can just simply trigger the test runs through GitHub Actions, and it will just cycle through.
Sounds good. The second question is pretty interesting. So I see that LocalStack is closer to AWS than KnifeMock, but does it close enough and substantially closer?
Yeah. This is a good question, right? Because yes, LocalStack is using Docker containers, but as far as I know, happy to be wrong here, there's probably still differences in the Firecracker execution environment that AWS is using under the hood or whatever. So it is possible theoretically to get closer, but we have not found anything better than LocalStack and not found anything close. And really, in those couple of categories that we were talking about, that mimicking cold start behaviors, being able to configure those account level AWS limits, we find that those are really, really valuable and enough justification on our own for us to use LocalStack. So, and I know the team's constantly working on getting closer and closer too.
Sounds good. This question came on our YouTube live chat from Dimitri. So Antithesis can be standalone.
What do you mean by standalone? Do you have any additional?
I guess this was the only comment.
Okay.
I guess since Dimitri is not with us on the chat, or maybe we can just wait for the response, so we can maybe move to the other questions that are on here. And yeah.
Maybe that question was somewhat related to talking about how we're testing a new service that we're building internally with Antithesis. So Antithesis in this context is our larger autonomous testing platform. We in this bug port that we revealed are talking about building an additional service to fit into that platform, but we are able to test that part of Antithesis inside Antithesis, and we also do test the entirety of Antithesis inside Antithesis, which my colleagues have a systems distributed talk on from earlier this year that's worth checking out as well.
Mm-hmm. Sounds good. I guess the follow-up came really quick. So can you run Antithesis on your local hardware?
Not really. So a lot of this happens in the cloud right now because the kind of boxes that are required to run this deterministic simulation testing requires, a lot of specific work that we've done on specific hardware and a boatload of compute power. But that's something that's interesting.
Sounds good. I guess we'll take up the last question for the day, and that would be, any known limitations or types of bugs that Antithesis struggles to identify?
Not specifically that I'm aware of. I mean, I think the one thing that maybe is a little bit harder is if you want to figure out stuff like business logic, you'll have to do additional work and introduce a sets of properties or user assertions packets and define this can never happen or this should always happen. But so far, I haven't seen any limitations that Antithesis in terms of bug finding.
That sounds pretty ambitious. I would love to try that out sometime. Cool. So thanks a lot, Gabriel and Ben for walking us through Antithesis. And for people like who want to explore more about LocalStack and Antithesis further, we have a blog post coming up. So just wait for a couple of weeks. We'll have something on our LocalStack website. So we'll definitely reach out to you once we have something up. So yeah, thanks again, Ben, and thanks again, Gabriel. I hope you have a nice rest of the day, and we'll see each other very soon. Cool. So going next, we have Rob with us, who is going to be talking about CockroachDB and LocalStack integration, comfort in chaos. Let's hear about it.
Thank you very much. That was an amazing talk from Antithesis. Thank you very much for that. That was really interesting. So today I'm going to give you a quick introduction to CockroachDB. I can't assume that everyone has heard of it. And then I'll be diving into two live demos. So wish me luck. Let's get cracking. Before I begin, I just want to thank Harsh and Valdemar from LocalStack, who've been super helpful in helping me with my LocalStack journey. The team have been amazing. So thank you very much for that. So CockroachDB was released in 2015 as a distributed SQL database, taking the best bits of relational databases, which is resilience or reliability perhaps, but not necessarily the scaling aspect, and NoSQL databases, which have done the scaling aspect really well, but historically have fallen short with the consistency. CockroachDB brings the two together in a package that also allows you to deploy on your own hardware, on cloud hardware, across clouds, or perhaps hybrid cloud, wherever you need to run. It's familiar to developers and database administrators. I introduced CockroachDB at a number of companies that I've been at simply because I wanted the developers that worked with me to be able to speak SQL to a database. But under the covers, it's quite different. It's a distributed set of nodes that operates atop a key value store, but it presents itself as a distributed database that looks and feels like Postgres. You can scale really easily with CockroachDB. It's just a case of adding nodes to a cluster. And as you add nodes to a cluster, the cluster gains volume for data, but it also gains the ability to increased throughput for reads and writes. As you add a node to the cluster, CockroachDB will automatically balance the data across the new nodes to ensure that you've always got good utilization of hardware. And to scale down, it's just a simple case of removing a node, and then it allows you to scale elastically with the ebbs and flows of the day and business. You can scale wide as well with Cockroach. You can scale beyond machines, data centers, AZs, regions, and you can also scale across clouds if that's your thing. This allows customers to achieve a high degree of resilience against failure. So if a node goes down, an AZ, a region, or perhaps even a cloud, you can survive those kind of outages because of the way that CockroachDB is distributed. And finally, you can pin data to locations. Let's say you have a centrally managed, globally distributed database. You can pin data to specific locations to give users to satisfy regulatory compliance with whatever jurisdictions you happen to be running in. So let's get going with the demos. I've got two. I'm going to run a live chaos demo, and then I'm going to integrate CockroachDB and LocalStack into my Go testing, just to show you how everything integrates. So my first demo is chaos testing. I'm running a K3D local Kubernetes cluster with multiple agents. On each of those agents, I've got a CockroachDB node. Nodes are all the same. There's no particular master node or read replica, etc. They all perform the same kind of job, and they're distributed across the cluster, as is Chaos Mesh. Now, I will be trying Antithesis if this allows me to do the same kind of thing, because that sounds really interesting. And I'll be injecting over here faults into the Kubernetes environment, like killing pods, introducing delays and dropping packets, etc., just to see how CockroachDB copes with that. So this is the test script. I've spun up the cluster already because that takes a while. I've installed CockroachDB and I've installed Chaos Mesh. And now I'll perform the chaos experiments. So let's just monitor CockroachDB. I've got 3 running instances, 24. They're all running on 24.2.0. I'll run an application, and this is just a basic Go application that performs financial transfers. Let's say it's a simple bank account application, and it records the amount of time that transaction took. Now let's perform a cluster upgrade. Over here, we've got the CockroachDB console, and we can see that there are 3 live nodes, all running 24.2. And up here, we see the main cluster version up here, 24.2. I'll update the version of CockroachDB now. You'll see that we just received a quick blip that was because the node that request was routed to at that precise moment was taken out of the cluster. So application retry logic is important in any situation, but that's the amount of downtime that we saw from updating one of the nodes to 24.2.2, and that was another node. So what we can see now is CockroachDB recognizes that it's running across multiple versions. There are 2 nodes on 24.2.0, 1 node on 24.2.2, now 2, and we can see that we've got 1 live node, 1 draining node, no under-replicated ranges, although I would expect that to go up now because we've got 1 draining node. And this is just performing the last of the updates. And then you'll see that this goes from mixed versions to just 24.2.2. So that's just finished. I'll give it a couple of seconds just to make sure that there are no under-replicated ranges. And what I mean by that, a range is simply a contiguous chunk of data that gets replicated across the cluster. So that looks happy now. Now let's perform some chaos experiments. First, I'll simulate a pod failure. So I'll run that experiment, and Chaos Mesh under the hood will substitute one of my pods for a waiting pod. So essentially the pod just goes away. So we saw another blip there, and the application continues happily. If I go over to the dashboard, you'll see that there's 1 draining node, and then there are the under-replicated ranges will go up because CockroachDB wants to have, with a default replication factor of 3 copies of each range or replica across the cluster, and it can't satisfy that with just 2 nodes. So let's go back to here, remove the chaos experiment. So that's back in the cluster now. And in a second, we'll see that the draining nodes are 0 and the under-replicated ranges go back to 0. So this is CockroachDB self-healing itself. I'll wait for those to go to 0. And, oh, sorry. Then we'll move on to the next one. Let's kill a pod this time. So now there'll be no grace period. I'm simply removing a node from the cluster. There was no blip in applications there, so the application was unaware of that change. But we do see a draining node, and there will be under-replicated ranges. So this could be a data center goes offline for any reason, or there's a power outage, or something quite severe happening. But as you can see from the application, it's largely unaffected. I'll delete that experiment, and I'll wait for any under-replicated ranges to go back to 0. There doesn't seem to be anything. And we'll move on to the next one. So now I'll run 2 network partition simulations, one symmetric and one asymmetric, which is a little bit more insidious. So I'll create the network partition, the symmetric network partition. And you can see that the application has faced a bit of a blip there. And if I come over to the networking tab, you'll see that node 1 is not able to talk to any of the nodes, and none of the other nodes are able to talk to node 1. This is a symmetric network partition in that neither side can communicate with the other. So the application is continuing with 2 nodes with the network partition in place. I'll delete that chaos experiment, and I'll wait for any under-replicated ranges again to come back to 0. And then we'll move on to the asymmetric test. So let's go back here, run the asymmetric test. So we see the application is unhappy again. It's having to retry some of those transactions simply because the nodes, the replication isn't happening between one of those nodes. But this time, 2 nodes are able to communicate with 1 node, and it might only be able to talk to one of them. There's asymmetry in that partition. So if we look at the network tab, it's node 1 again. I didn't pick node 1. I think I've randomized it, but it's not able to talk to the cluster. And as a result, we would see under-replicated ranges once that screen updates, but the application is happy. I'll delete that one. And we'll move on to the next one, which is packet corruption. Let's say for some reason there's a networking issue in your data center or in AWS, GCP, Azure, wherever the case may be. And I think in this case, I'm simulating 10% of all packets between myself and CockroachDB and between all of the nodes within CockroachDB. 10% of the packets I'm just corrupting. So we can see that the application is largely unaffected by this. We might see a slight blip in network because, as you can see, they average typically around 0.75 milliseconds to talk to one another on my local machine. And we're seeing higher latencies because of that retry that's happening automatically. I'll delete that chaos experiment. and we'll move on to the penultimate one, which is packet loss. So 10% of packets in this example, I'm just dropping. So we see that the application did have to retry a request just then, and it might have to retry every now and again because some of its requests are being dropped. And again, we'll see that there's a slight network delay between the nodes because of those automatic retries that are happening. I'll delete that again. And now I'll simulate a network delay. I'm injecting 10 milliseconds worth of latency between all nodes. And you'll see that we're not actually seeing much of a delay, but I think on average, we've probably gone up a little bit. We're seeing a couple of request round trips that are taking towards 40 milliseconds now. And that's because there is a delay between all the nodes. You'll see here, there is a delay, but overall the cluster is happy. If the delay to a particular node was to be significant enough, the node would be taken out of the cluster. And similarly, I know that Antithesis mentioned it. If time drifts too far from one node, that node will also be taken out of the cluster because it can't trust the data. So let's kill that last chaos experiment and move on to the next. In the next test, I'll be using Docker Compose to run a suite of application tests with LocalStack and CockroachDB. The flow of communication will be the test code inserts data into CockroachDB, a CDC event, a change data capture event. Change data capture is built into Cockroach, and I'm using that to write an object into an S3 bucket. Then the application will wait for that object to be available in S3, and if it is, the test passes. If it times out, the test will fail. I'm implementing this in, I think it's Gherkin or Cucumber, I can't remember what the name is, but I had to dust off my skill set here. And essentially, I'm testing order creation. When a customer places an order, the order is available in S3. I create the bucket in LocalStack. The customer creates the order, that's the insert into the database, and then I check that order that I created exists in S3. Now, this is what the compose file looks like. I'm using LocalStack. I'm spinning up Cockroach. I'm spinning up an application that runs the tests, and the tests are simply like this. I have an integration flag that denotes whether the application, the tests are running in integration mode or unit test mode. I have a test context, which holds my database and S3 pointers, which is essentially just instances of a connection to the database or to S3. If I'm running with integration tests, I create the test context with the database and S3 connections, connecting in the same way that I would in my production code. I run them, I capture the exit code, and then if I'm running integration tests, I close the connection to the database. I have a unit test in here, which asserts that I can read an object in S3, given a simulated object. And then I spin up my integration tests if I need to run them. So for example, here I've got my test features. This could be called anything. And I skip the test if it's not an integration test. Let's stop that test there and run my unit tests. So this just runs I cd into the integration test directory and run go test. And if you look down in the run, you'll see that I skipped the test features unit test because it's an integration test and I didn't request integration tests. Now let's do the same thing again, but integration tests this time. And this time I pass more information. I'm spinning up Docker Compose. I'm building my application and I'm outputting a test executable. And that test executable is being used. It's connecting to the database. It's waiting for, so it's connected to the database now. It's connecting to S3. It's created the order. So then I create the bucket. The bucket gets sent a message from CockroachDB. And then I perform a test that asserts that everything is as I expected it. So that's a round trip from the application code through LocalStack's S3 and then back to the application. I can run it again. It's all very quick. It can be run locally without an internet connection, provided you've got the Docker images. And it allows for things like CI/CD pipelines. You can test a much richer section of your application thanks to LocalStack. So let's go back to the slides and just finish off with some key takeaways. So for me, I've been using LocalStack for a number of years, and it's been an absolute godsend to me at a bunch of different companies. I've probably saved an absolute fortune in forgotten infrastructure in AWS. And and been able to test cloud integrations, not just for S3, but for a suite of other tools, thanks to the tool. CockroachDB is currently powering some of the largest workloads for some of the most well-known brands in the world. I can't talk about all of them, but they are very exciting. And you can create your own, if you scan the QR code there, you can create your own multi-continent clusters completely for free just to get started, to kick the tires. Also, there's a video library in YouTube where I appear in a lot, unfortunately, so you'll have to listen to my voice a little more. But feel free to scan those QR codes, create your own clusters, and have fun with it. Back to you in the studio.
That sounds good. Thanks a lot, Rob, for walking us through the entire presentation. We have a couple of questions coming in from folks. The first question that is coming on top is, can we run these chaos tests locally on a CockroachDB if we are running it ourselves? I guess this
Yes.
question is more about local execution. Yeah.
Yes, absolutely. So everything I was just running then was all local. I was running local nodes of CockroachDB. I was running LocalStack locally, and I was running Chaos Mesh locally. So you can absolutely do it. I was choosing to do it in Kubernetes because it allowed me to expose a load balancer from within Kubernetes. That allowed my application to focus on one endpoint and have Kubernetes distribute to whichever CockroachDB node was available. Now, by default, every node in CockroachDB will handle traffic. We call that the gateway node. But every node is capable of doing it, and all requests will be distributed across it, hence the need for a load balancer. So yes, you can absolutely do it. You can also test your cloud clusters as well. So if you wanted to perform some chaotic testing in your cloud clusters, you wouldn't use the same tool set for this, but it is possible. So yeah, either self-hosted or self-hosted on-prem in the cloud on your machine, or using our managed service, you can absolutely test it in chaotic ways. And I think you should. I've never been in a situation where prior to CockroachDB, I wanted to run chaotic tests on my database because the database was always there to be protected. But actually, it's quite liberating to work with a database that embraces that kind of chaos. You feel a lot more secure with it.
Sounds good. I guess the second and the last question for the day is a bit unrelated. It's about how does CockroachDB compare against Aurora and or Azure Cosmos?
Yeah. So they're different paradigms, really. So Aurora is a Postgres or MySQL database that is in the cloud. And Cosmos, I think, is maybe Vitesse. Correct me if I'm wrong. CockroachDB was built from the ground up to be a distributed SQL database. So there are differences there, but also in the way they scale. I think Aurora scales by using multiple read replicas, which allow you to scale up for reads, but there's a single write node. So you're not necessarily scaling up for writes. So that might be a single point of failure for writes, whereas CockroachDB doesn't have any special differentiation between nodes. So every node can perform tasks within the cluster.
Sounds good. I guess we have one other question that just popped up right now. And this is about how CockroachDB guarantees for eventual consistency compared to Google's Spanner.
It's actually the other way around. So with CockroachDB, you're guaranteed consistency across the cluster. Whether your cluster is within a single cloud region or data center of your own or global, the default isolation method in CockroachDB is serializable isolation. So you're guaranteed that whatever you put into CockroachDB, you'll be able to read back out as expected. You can opt in to slightly stale data. Let's say you've got a table that is very read heavy and you don't need completely up to the second latency, perhaps 4.2 seconds, I think it is, latency. You can use a table topology for that in the same way that you would use a different table topology to partition data. And that can help with additional read throughput as needed. With Google Spanner, and I might be wrong, but from what I understand of it, there's a write node which will replicate data to read replicas. So you might face eventual consistency there, but you wouldn't face eventual consistency in CockroachDB unless you explicitly asked for it.
That sounds good. Cool. I guess this was all of the questions that we had for the day. So thanks again, Rob, for being present at this meetup, sharing your insightful notes, and showing us how you can use CockroachDB with LocalStack and much beyond than that. So yeah, thanks again, and I hope you have a great rest of the day.
Thank you.
Talking of which, we are almost at the end of the session for the day. The one final note that I would like to share is that LocalStack 3.8 is out, and this particular release offers a lot of new features and enhancements that you would definitely want to try out. Some of the things that I can highlight on top of my mind is the new API Gateway provider, a new event source mapping implementation, several new features for Lambda, step functions, and there are so many other updates in various other AWS providers that we are providing right now. If you want to check this out, you can definitely visit the link that is right on the YouTube live chat, or you can just go to blog.localstack.cloud and you can just check it out right over there. So this particular release will be the last one before our next major release. And I guess Trump's role, this is going to be the 4.0 major release that we would be rolling out. So stay updated, keep an eye out, and this would be packed with some of the best features that you have ever encountered in the LocalStack platform. So join our Slack community or check out our social media channels, and definitely reach out if you want to get a sneak peek around these particular features. With that said, I will bid goodbye to everyone else, and maybe I'll see you in the next meetup around here. Have a good day, folks, and see you around.